Hello friends, good afternoon and welcome to the EduSat Network. Our topic of discussion today shall be GIS and Glacial Environment. We shall be talking about the use of Geographic Information System in the Glacial Environment. And friends, for this very lecture we have with us today Dr. Pankaj Kumar, Assistant Professor, Department of Geography, Delhi School of Economics, University of Delhi. His specialization also includes GIS and mountain environment. And friends, with this I welcome sir to our studio. Sir, thank you for
Good
coming.
afternoon everyone, and my today's lecture is based on the GIS and the glacier environment. Why I have selected this for the today's lecture? Because GIS is a very important or handy tool in studying of this remote located glacier environment. If you will go to study this glacier environment, as far as my study area is concerned, it is lying in the western Himalayan region, and where the glaciers are found above the height of 4,000 meter. So, and the harsh condition and the approachability problems is very much. Therefore, we have to rely on an information source which without being in touch with that area, we can access the information and we can map the area, we can utilize the information. That is why this GIS is a very handy tool in accessing and studying the dynamics of the glacier, like snow cover, the glacier lakes and all related issue we can easily access and we can easily understand with the help of remote sensing and GIS. The one of the basic point here, or we can say the important thing, that this remote sensing and GIS gives us a picture or the map of the area with in a temporal framework. So, we can go for the change detection also, and without much investment we can have a synaptic view of that area in a temporal manner, which will be helpful for understanding the glacial environment. The second thing, because in Himalaya is also it is a border area, so the basic information related which lie in the topo sheet is not easily available to everyone. So, we can rely with the information of the other source like satellite image to study that area. So, glacial environment is a very good source of the study of this glacial environment is GIS. And the today's topic here, I will explain how we can go for mapping the snow cover change in the area and some of the glacier lakes and the related issue we will discuss. So, before going to discuss these things, I would like to go by the introduction of these things. Like in Himalaya, if we will see the Himalayan environment, it is now degrading, and the Himalayan region, because of its fragile geomorphology, geology, highly variable climatic condition, steep slopes and great altitudinal variation, the fragility and vulnerability increases. In this 20th century or the first half of the 20th century, you will see that tremendous impact on high mountainous vulnerable glacial environment because of this climate change. So, many of the glaciers are melting rapidly and giving a birth to the formation of a large number of glacial lakes. These lakes sometimes burst and create a phenomena of glacial lake outburst flood. So, the accurate and timely information on the spatial location and regular monitoring of the dynamics of glacier lakes is needed to present and monitor the globe hazards and assess the damage to be occurred in the future. So, the remote sensing and participatory GIS play a greater role in the study of the remotely located glacier environment, because the approachability is a big problem and the harsh climatic condition does not allow us to go for the conventional survey, and it will take a long time and also the huge money is involved if we will do the conventional survey, and it is not possible by a few person and an individual person to do the survey of the whole area for studying of the snow cover and for studying the or mapping of the glacial lakes. Therefore, our reliable data is the remote sensing, and GIS provides us a technique where we can analyze this remote sensing data and we can derive as per our need the information available in that remote sensing data. So, we have the free satellite images available on a GLCF site which we have taken, the Earth Explorer and Globis, and also our Bhuvan portal is giving us free data which we can use for our research purpose. And if we will see the relationship between the climate change and the glacier melting, we will see that we have a cyclic trend that the climate, if the melting will take place, the melting will result into the glaciers and snowpack melting will result into the decrease in the surface area of the snowpack and the ice, which will decrease the albedo of the ice and snowpack, which is going to affect the greater absorption of heat and energy by exposed surface, which will again result into the decrease or increase in the temperature as a result of the climate change. So, here we have a cyclic pattern, like one is going to affect the other. If climate change, if the change in the temperature will be noticed, then what will happen? The surface area, the temperature of the surface area will increase, and this temperature of the surface area will result increase in the temperature of the surface area will result into the melting of the snow, and that is why we are seeing that most of the glaciers in the Himalaya are melting fast and receding, and at the snow out position they create a temporary lake, and sometimes these lakes becomes bigger and bigger because of the feeding of these lakes by the melting water, and because of instability of this region and because of fragile ecological condition, the geological condition, if certain this fracture zones are passing from nearby that lakes, the vulnerability increases. And what happens, sometimes these glacier lakes burst and create a huge mass exodus of water from these lake to the low lying areas, and so a flooding situation take place in the mountain. So, we are trying here to see the nature of the snow cover, like what was the earlier condition and what is the present condition. So, for that we have taken a data set of year 1989 and 2011, and from the we have mapped the snow cover of the data of 1989 and 2011, and then we have analyzed and tried to find out how much snow cover has been decreased and how many glacier lakes has been formed in that area. The government organization, international government organization, this EC mode is working in this area, and also the GSI, Geological Survey of India, is working in this area, and they have identified too many glacier lakes being formed in this last 2 and 3 decades in this mountain environment, and they are making vulnerable the low lying population residing in the valley of this river basin flowing in that area. So, it is now a very pertinent topic to understand the dynamics of the glacier. My study area is basically the Himachal Himalaya, the whole Himachal Himalaya I have taken, which is having 12 districts, and for the study of the glacier and the snow cover, we have taken only the 3 districts, uppermost districts, this Chamba, Lahaul and Spiti and Kinnaur, which is mostly glaciated regions, and the elevation zone has been demarcated here. So, for the general picture of the study area, geographically the Himachal Pradesh is situated between 30 degree 20 minutes 44 degree to 33 degree 12 minutes 40 degree north latitudes, and 75 degree 45 minutes 55 degree to 79 degree 4 minutes 20 seconds east longitudes, and covers a geographical area of 55,673 square kilometer, which is about 1.69% of the total India's total area, and it extends from the Shivalik hill in the south to the greater Himalayan range, including a slice of Trans Himalaya in the north. The state is compact in the shape and almost wholly mountainous, with altitude varying from 300 meter in the plain of Kangra and Una to nearly 7,000 meter in the high hills of Lahaul and Spiti. So, the variation in this altitudinal zone gives us that which type of climatic condition we have. If you will cross the longitudinal, if you see the longitudinal profile of the Himachal Himalaya, you will find that we have all the altitudinal zones, and so we have different type of climatic pattern in the mountain. below 1000, 1000 to 2000, above 2000 to 3000, 4000 and above, we have a different type of zones and we have different type of climatic conditions. The data source for the present study is basically the survey of India toposit of 1:250,000 scale, which has been taken for the reference purpose. Then we have taken the satellite image Landsat TM for August September 1989 and 2011 of 30 meter spatial resolution, which is freely available from GLCF and Earth Explorer and Globis site of US Geological Survey. Then temperature and rainfall data of Bhuntar and Manali, Dharamsala and Mandi for 1977 to 2007 has been taken, which is 30 year and quite enough for seeing the climatic pattern, like what is the pattern of the rainfall and temperature in this area. It has been taken from India Meteorology Department, Pune. And subtle radar topographic mission digital elevation model, which is known as SRTM DEM of 90 meter spatial resolution, has been taken from GLCF. And also this DEM of Bhuvan portal, which is Cartosat DEM, has been taken also for from this Bhuvan website, downloaded and has been used in the study. The Google Earth image has been taken for the reference purpose and has been used for to show the area to the in a nice manner. Then the primary survey of 150 respondents from 6 villages along Simla Kaja Manali road during June July 2010 and 2011 has been performed, and from there we have classified and then we have find out the results and we have analyzed their respondents view regarding this. So, the satellite data coverage which we have used in our study, basically these are the tiles which covers the whole Himalaya. The Landsat TM which I have taken for my study, the Landsat TM is 8 Landsat TM tiles covers the whole Himalaya. So, all these 8 Landsat TM has been downloaded from GLCF, and then we have converted them into the FCCC TM by after stacking all the bands of these images. We have prepared this FCCC for false color composite for year 1989 and false color composite for the year 2011, and then we have performed other analysis. For that, for better understanding, I will explain the methodology. For a spatial temporal analysis of the snow cover and the glacial lake, I have used the toposit of Survey of India. From this toposit is used for reference purpose. Landsat TM has been used primarily, and this Landsat TM, the pre-processing, image pre-processing were done, the geometric corrections and the radiometric correction were performed. Then we have we mosaic the whole image to cover the whole Himalaya. Then area of interest were subsetted from that image using the IRDAS imaging software, and from there after that we have performed this NDSI, NDWI and NDPI. As far as the reports and articles are concerned, the secondary sources are concerned, we have taken it for the reference purpose also, but SRTM DEM has been used quite extensively for seeing the elevation zone of the study area. Before using this SRTM DEM, we have performed the wired correction in this SRTM DEM, and also we have adjusted the error in the height elevation in this SRTM DEM, and then from that SRTM DEM we have calculated the slope, aspect and this land cover with the help of this SRTM DEM and Landsat TM, and then we have used this all these data to analyze and to find out the result with the help of the indices. 3 indices I have used. One is the NDSI, which is known as normalized difference snow index for demarcation of the snow cover, and then for demarcation of the glacier lake I have used this NDPI, normalized difference pond index and normalized difference water index. So, for that we have used different bands of this Landsat TM. Somewhere we have used the ratio of the band 4 and band 1, somewhere we have used the ratio of the band 5 and band 2, band 4 and band 3. So, according to the need, like if we are using this NDSI, then we have to go for this green minus short wave infrared divided by green plus short wave infrared. For NDWI, we are using this NIR, NIR minus blue divided by NIR plus blue band, and for NDPI we have used this MIR mid infrared minus green divided by mid infrared plus green. So, for NDSI we have used this indices, and for demarcation of snow cover area from the non snow cover area we have used a threshold value of 0.4. So, all the this value lying above 0.4 is coming into the snow cover area, and below that is non snow cover area. Likewise, we have clubbed the result of this NDPI and NDWI. Whatever the results, the indices we have performed, and then we have stacked the both of the images, and from that images we have taken a sample, and from that sample we have demarcated the threshold for demarcation of the water body in that area, and that threshold has been used to demarcate the glacier lake in that whole Himalaya, primarily the 3 districts, upper districts, this Chamba, Lahaul, Spiti and Kinnaur. And then snow cover change has been analyzed to see, after seeing the results of the 1989 and 2011. Likewise, I have also used to see the picture, what is the picture of the glacier lake, how they are increasing. So, 2 big glacier lakes has been taken for the case study, which we will further see. So, for better understanding of the Himachal Himalaya, the digital elevation model, with the help of the DAM, we have prepared the elevation zones, and 7 categories has been demarcated here, and we can see also the this longitudinal profile of the Himachal Himalaya, like how it crosses. So, Himachal Himalaya is not having only the plain area, but also it is touching the height of the 7,000 meter, and it is covering the Shivalik Himalaya, the middle Himalaya, central Himalaya, and also some of the portion of this trans Himalaya region, which is the cold desert. And in Lahaul, Spiti and Kinnaur districts and the Chamba, upper parts are like that. So, my study area is having this trans Himalayan zone. Land cover of the 2011, the 4 category has been taken to demarcate the land cover. One is the forest cover, snow cover, barren land and water body, to see the general picture that where is the forest is lying, where is the snow cover area, how much the barren area is there. So, we see here that most of the area is the forest cover, then we have the barren land, and this snow cover is coming to third in this line. So, if we will see the snow cover map, which is prepared with the help of the NDSI for year 1989 and for year 2011, we will see that in the 1989 quite extensive area was covered with the snow, and in 2011 we see that the very less area is covered with the snow. If we will see the figure, then and the threshold value, as I have already explained, that 0.4 has been defined for snow, which has been taken by Jiao at L 2001. He has done a study in the Tibet Himalayan region, more or less similar to my study area. So, I have taken that threshold value, and if you will see the data, then from 1989 to 2011, around out of the total geographical area, around 9% area of the snow cover has been deglaciated. Means the snow cover of 1989 was more, and in 2011 it is less, 9% less to the total geographical area. So, if we will see the data here, if we will see the change here, then the aerial change from 1989 to 2011, in picture it is quite clear that in southern and eastern part of the Himachal Himalaya, the southern and eastern portion, where we have the maximum change, we are seeing the red portions, and also in the upper northwestern part we have the change, but all the green portions we have a very less change in this middle portion. So, altogether we have, if we will see the data, the 9% coverage. Earlier in 1989 the snow cover area was 17% of the total area, but it decreased to 9%. Non snow cover area increased from 83% to 91%. So, we see here a drastic change and decrease of snow cover from 1989 to 2011, which is a concern for the researcher, that why this change is taking place. Is this the result of the climate change or some other factors are involved? Right now, as far as the global body is concerned, they are basically saying that the climate change is the main problem due to which this snow cover is declining. And when this snow cover declines, if we will see the this snow cover study of a specific area, then also in all the districts, Lahaul and Spiti, Kinnaur and Chamba, we are seeing the same pattern, which we will see in the next slide. So, determination of snow line altitude was also performed in that area. For this, for the determination of snow line altitude, I have taken 5,000 samples of the data, like I have taken 5,000 samples of the height which has been picked up from the outer margin of the map of the snow area. So, snow area has been demarcated, and from that snow area, what are the last point where the snow has been seen has been taken. So, for all the readings of the 5,000 points has been taken, and it has been averaged, and the average value is showing that there is the shift of snow line from the lower area to the upper area, which is around 240 meters in from 1989 to 2011. And in this inset map, it is quite visible that these are the three prominent area where we see the snow line altitude shift, and the snow line altitude has been shifted quite extensively in the upper area of the valley. So, then if you will see the district wise inventory of the snow area for this Chamba district, this red circle is showing that these are the prominent area where we have the we are noticing the change. The one image is for year 1989, another is for 2011, and the change, snow cover change is also shown here. So, category wise distribution of snow cover was performed here. Earlier, for the whole this 3 district and the whole Himachal Himalaya, we have just performed the task of snow cover mapping, but here we are taking the category of snow also, like frost, fine granular, medium granular and coarse granular, and each category separately we are mapping, and we are trying to get the data of 1989 and 2011 for this category, and we are and it's a quite similar trend we are seeing here also, that all the categories are showing a decreasing trend. If you will see the frost in 1989, 4% area was frost covered, but in 2011 for the same period it was only 2% area. The fine granular snow was also decreasing from 7 to 2.3. The medium granular was also decreasing from 1 to 0.1. So, and non-snow area is increasing. So, it was 88% of the total area in 1989, which has increased to 95.6%. So, a total of around 7.6% area decrease in the snow cover has been noticed in this Chamba district. As far as the Lahaul and Spiti district is concerned, the same scenario is being repeated here also. If we have seen that the frost area in 1989 was 11%, which has declined to 5. Fine granular snow was 20%, but it is there only 10% in the 2011. And medium granular snow is also showing decreasing trend. Coarse granular is mostly absent in that area. So, a total increase in the non-snow area is around 17%. And if we will see the map, we can see that the snow cover area of 2011 and 1989, the change is quite visible by this map. If you will see the Kinnaur district also we have the same trend, and the figure are also more or less same for the Kinnaur districts. Then we can see the retreat of glacier in the Himalaya, like how much glaciers are retreating, how many, we have the data from GSI, Geological Survey of India. Some individual scholar have also worked, like Srivastava et al. In 2001, Nathani in 2001, D.P. Dobhal, Oberoi, Nanwal et al. In 2008, and I have compiled from their results that if we will see the condition of the glacier of the Himalaya, it is alarming now, and all the glaciers are showing a retreating trend. So, if you will see the Pindari glacier, it is showing a retreating trend, and the retreat is 23.4 meter per year. The Gangotri glacier is showing retreat of around 20 meter per year, but the retreat is maximum now from in between 1996 to 1999, which is 25.33 meter per year, and it's a cause of concern for the Gangotri glacier. Then the Barasingri glacier in my study area, if you will see the data here, it is showing 31.28 meter per year in between 1956 to 1963, but the trend is increasing. Like if you will see the data of 1977 and 1995, this decrease is 36.11 meter per year. Also all the glaciers which has been listed here, altogether 22 glaciers or glaciers are showing the decreasing trend in the Himalaya. If you have to see the status of glacier in the different river basin of Himachal Himalaya, which is my study area, then it has been demarcated in river basin. There are Spiti, Parbati, Chandra, Miar, Bhaga and Baspa river basin, and according to the river basin the study has been conducted, and if we will see the Spiti river basin, 337 glaciers has been studied. Out of these 337 glaciers, 16% loss in the area has been noticed. During 1962 to 2001, the area of glacier was 474, and in 2001 it was 396 square kilometer respectively in this Spiti river basin. So, the status if we will see the status, 169 showed the retreat. So, 50% has shown the retreat trend in the Spiti river basin, and the rapid retreat after 2001 has been noticed, and this is the highest among all the basins of Himachal Himalaya. Same pattern is there in the Parvati basin also. For Chandra basin, where the Barasingri, Chota Singri, Hamta and the Samudra Tapu glaciers are there, 20% less in the area has been noticed during 1969 to 2001. And for Miar basin, which is one exceptional this trend which has been shown here, like 165 glaciers had been monitored between 1962 and 2011, where 80 showed the retreat, which is 49%, but 78 has shown advancing trend. So, 7 had shown no change in the glacier area. So, this is one exception that 78 glaciers are here showing a advancing trend. As far as the Bhaga is concerned, 111 glacier has been studied, and most of which is located on the Manali and Leh road. 30% loss in the area has been noticed in the from 1961 to 2011. In 1961, the area of the snow cover glacier was 363 square kilometer, which has been decreased to 254 square kilometer in 2001. So, 108 glaciers have shown a retreat trend, whereas 3 do not show any change. Overall, 98% has shown a retreating trend. In Baspa river basin, 19 glaciers monitored between 1962 and 2001, and area in 1962 overall area was 173 square kilometer, which has decreased to 140 square meter in 2001. So, overall 19% loss in the glacier area has been noticed. So, this study has been performed by Snow and Glacier of the Himalaya Division of and it's a joint project of MOEF, Ministry of Environment and Forest, and the Department of Space Application Center, Ahmedabad. So, my study, which I have earlier shown here, is also showing the similar trend of retreat of the snow cover in my study area. As far as the glacial lakes are concerned, we have some of the picture of the glacial lake, the Chandatal lake in the Chandra valley of Lahaul and Spiti. Then we have Surastal lake or Bhaga valley, Lahaul and Spiti districts. What are these glacial lakes? First, we have to understand that when this glacier melting take place, at the snow out of the glacier, where the glacier melts, the snow out of the glacier, a vacant space is created because of the melting of the glacier, and this rapid melting of the glacier is creating this vacant space, and this vacant space is being filled by the melting water, and moraine dam which has been eroded by these glaciers create a dam like situation, and behind that dam these glacier lakes are forming. In initial stage they remain a very small, but gradually because of the melting of the glacier in behind in the background areas, and this melting of the glacier resulting into providing the more and more space, open space for formation of this glacier lake. Also the melting of the glacier is providing water which is being accumulated in this glacial lake area. But this glacial lake area are now increasing. A large number of glacial lake has been reported into this Himachal Himalaya, also in Uttarakhand, also in this Lahaul, Sikkim areas and Bhutan. So, EC mode has mapped the whole Himalayan region the glacial lakes, and they have also said that the number of the lakes is increasing, and it is quite the increasing trend is very prominent in this last 2 decades. So, I have also tried to map these glacial lakes in my study area, and these glacial lakes are very dangerous because these moraine dams behind which these glacial lakes forms are not cemented, and that is why these are unconsolidated materials. So, sometime because of the pressure or because of the earthquake or something, some disturbance takes place in these glacier the moraine dams, and this disturbance results into the breaching of these moraine dams, and breaching will result into the mass exodus of water from this glacial lake, and this mass exodus of water result into the flooding situation in the low lying area. So, the human being and the animals and all the infrastructures are on the stake when this type of lake outburst take place in the Himalaya, upper Himalaya. So, this normalized difference water index has been performed, which is based on the philosophy of normalized difference vegetation index, because the both are same, but only the band changes here. So, NDWI uses band NIR minus blue divided by band NIR plus blue, but when we will take the Landsat image, it becomes the TM1 and TM4. So, TM4 minus TM1 and divided by TM4 plus TM1. This is the formula of NDWI. In NDPI, the formula changes and it becomes TM5 minus TM2 divided by TM5 plus TM2. So, these are the Landsat bands used for NDWI and NDPI, and TM1, TM2, TM4 and TM5 has been shown here. All the image, all the this path and row slice has been stacked, they have been mosaicked, and then from that mosaic the Himachal Himalaya has been subsetted, and these bands has been used for further analysis. So, inventorying of the glacial lakes of Chamba, if we will see here, around 17 glacial lakes has been identified in the Chamba with the help of this technique. Likewise, Lahaul and Spiti also having this, we see here that in the Lahaul and Spiti also the it's a image of the September-November 2011, we have seen that around 30 glacial lakes has been identified in the Lahaul and Spiti, and 2 glacial lakes are very prominent. In figure you can find out like 3 insets are there. One inset is with the Samudra Tapu glacial lake, another is Gipangat glacial lake, and in the background we have this Chandatal lake. So, the Samudra Tapu glacial lakes is increasing day by day. Likewise, this Gipangat glacial lake also increasing day by day. So, we have tried to identify like how much growth has been taken place in these two big glacial lakes, because they can pose danger in the future, and the approachability is very much concerned in that area. We cannot approach each and every lake in the area. So, I have identified these two big lakes for personal visit and for a detailed study. So, a case study is also given here, like case study of the glacial lakes of Samudra Tapu Glacier and Gipangat Glacier. The image, the upper portion map is showing the position of the Samudra Tapu Glacier Lake in the Google imagery, and for showing the nature or seeing the expansion trend, like how much area is increasing day by year by year, we have taken a satellite image MSS of 1976, and then we have taken the TM for thermal mapper for this 1989, and then we have taken image of this 2011. So, all these three images has been downloaded from this GLCF site or Earth Explorer. From MSSS we have tried to identify, because MSSS resolution is very coarse, but resampling method has been used to make them consistent with the image of 1989 and 2011. So, MSSS area has been identified for 1976 of this Samudra Tapu Glacier. From 1989 the Landsat image has been used to identify the area. For 2011 this Landsat TM has been used to identify, and then superimposition of each year area has been done in the and we are seeing here that a very high increase in the aerial coverage of the Samudra Tapu Glacier. It more than 150% increase in the total area has been noticed in the Samudra Tapu Glacier, and the personal visit by our team has also noticed this, that quite good this the lake Samudra Tapu Glacial Lake, the size of the lake is increasing, the volume of water is also increasing. So, we have to be concerned for this lake, and we have to monitor it time to time with the help of remote sensing and GIS, and also by field visit. The same task has been performed for the Gipangat Glacial Lake. For the Gipangat Glacial Lake also, this MSSS of 1976, the TM of 1989 and the TM of 2011 has been taken, and from that the this glacial lake NDPI, with the help of this NDPI and NDWI method, the glacial lake has been identified from the non-glacial areas, and then the mapping, the digitization work has been performed to map the area of the glacial lake for this individual period, and from there, and then after that superimposition of all the years area has been done from for 1976 to 1989 and 2011, and it is quite visible in this figure that the area has increased more than 167 times. So, we can see here that these two glacial lakes are quite prominent in that area, and they are concern for the future research work, and the government should also focus on monitoring this area by some government organization or research organizations. So, a case study of Parichu lake outburst has been given here. This is the this location of the Parichu lake. What's happened? This Parichu lake is not in India. It is lying in the Tibetan part of the China, and this Parichu lake, because of the moraine dam on the where the Parichu lake drains the water, the moraine dam blocked that portion, and because of that blockage the water accumulated behind this moraine dam, and which gradually the size of that in this lake was gradually increasing, and in 2005 on 26 June it resulted into the outburst, and this outburst created a havoc in the Indian part, because it is flowing also in the India, and it's a tributary of the Spiti river. So it joined the Spiti river near Sumdo, which is given in this shown in the map, that this is flowing in the Tibetan area and then coming and joining it at the Sumdo. So it becomes the part of the Spiti river, and most of the damage has been noticed in the Spiti river area. So this is the location and the map of the Parichu lake. The map is from this figure is from this Google Earth image, and this is the Indian location. You can see in the location that in Himachal Himalaya it is entering near the Sumdo and becoming part of the this Parichu river become part of the Spiti river, and then Spiti river comes and join to the Satluj river near Khab. So after that it becomes the part of the Satluj. So this created a damage during the outburst. Here we will see the change in the volume of the water of this Parichu lake. So if we will see here, see the Parichu lake outburst, the spatial nature of the lake before and after flood. If we will see here the result, like 16th April 2004, the lake was very nominal in size, not very big, and the lake area was like 20 lakhs 6,456 square meter. But in May 29 May 2004, the lake area is now becoming bigger and bigger from that part, and 26 July 2004, the lake area is now becoming more bigger. 14th August 2005, we will see the size has increased quite extensively, and on 26th June 2005, there was a breach, and after the breach we have the image of 6 September 2006, when we see here that the size of the lake has been reduced. So, and this has resulted into the outburst. So, water discharge has been also given here. The Gupta and Shah in 2008 in his own research work has shown that there is a water measurement point at Khab, and you will notice that that water measurement point is showing a high amount of water discharge during the year 2000 and 2005. So, because in 2000 also a small this outburst taken place somewhere in the mountain which was not noticed, but in 2005 the discharge station was washed away. So, there is no measurement data after a certain point. So, the water discharge during growth was the discharge measured at Khap on 26th at 10 am was 834 cubic meter per second. At 11:35 am, the water level rose to about 20 meter. After that, the discharge station was washed away. It is calculated that the discharge during this globe was about 2000 cubic meter per second, and lake volume and the Qmax calculated was this much cubic meter and 1007 cubic meter per second respectively. So, we can see here that and for the calculation of the Qmax, we have used the Clogg and Matthews formula in our study, and we have tried to see the flow pattern of the river, normal flow pattern of the river in that area. If we will see the normal flow pattern of the river in that area, then all the rivers is flowing more or less 100 cubic meter per second even in the peak discharge season. So, if the amount of water in the river is more than 100 cubic meter per second in that area, then it can be termed as a globe. So, whatever if Qmax is more than this 100 cubic meter, if the water is not being accommodated in this river body, and the height of the water is increasing more, then it can be termed as a globe phenomena in that area. So, I have identified certain globe also, like certain dangerous lakes which can be the future globe in that area with the help of this Qmax data, and with the help of this Qmax we can also mark that these are the prominent glacial lakes, and these glacial lakes we should consider for the future research work for their monitoring and regular visit to that glacial lake and mapping with the help of the satellite image and all. So, now these are the damage caused by these glacial lakes. If you will see the map here, A is basically near this is a water body, this Spiti river, and this Spiti river is flowing in that area, and this is the Salkhar area, where we have seen that the plantation was being damaged because of this water flow, huge water flow. And the second B image is the Leo village. Leo village is in the Spiti river near flowing. Leo village is situated on the bank of the Spiti river. So, the red portion is showing that this much area has been damaged because of the flow of the water. In the sea, we can see here that the Parichu and the Spiti, both the river are flowing and meeting together, and this one is for Sumdo bridge, which was washed away. And when the bridge was washed away, the connectivity from of Sumdo from the Salkhar was basically for one or more than 2 to 3 months it was disconnected. And Sumdo is a big military settlement of Indian government side. So, we have to provide the this connectivity as soon as possible. For that, the people started making a narrow this path road, track road, and with this track road they can communicate it to the Salkhar. So, a very huge damage we are noticing here in this Sumdo area, or the bridges and the road were damaged and the connectivity was lost in that area. So, this glacial lakes in the mountains are very dangerous, and we have to analyze the area, like how we can go for monitoring this in a better manner, and for that we need the high resolution satellite image. If you have the high resolution satellite image, with the help of this high resolution satellite image, we can generate the 3D model of the glacial lakes, and this 3D model will help us to identify how much water exactly is lying in that particular glacial lake. And with the help of this data, like volume of the water and the area, then we can model that if this lake outburst will take place, how much water will be released into the river after the glacial lake outburst. So, future scenario we can predict, and how much water level will remain in the valley, and at what time this will reach to the certain village, and at that village how much water will remain in the this river valley. So, a 3D modeling is possible for the whole area if that glacier lake has been identified as a problematic glacier lake. So, 3D modeling, with the help of this 3D modeling, we can generate the future scenario, like if the water level is 50 meter height, if the water level in the river is 100 meter high, if the water level in the river is 200 meter high, then how many villages we have to vacate, and how many villages we have to locate to the upper location to minimize the damage. Therefore, if you will see this Leo example, after this outburst and the damage caused by this Parichu lake outburst, the government started shifting the village of lower village into the upper Leo village. And now, if you will visit the area of Leo village, then you will find that most of the settlement has been shifted to the upper Leo village, because maybe in future the government is trying to avoid this type of situation in future. So, and it's a big apple and pea cultivation ground. That is why if you have the damage, that damage becomes very economically very huge. So, even the road and the bridges are being damaged. So, the connectivity is also a big problem. So, when this type of things happen, that is why the government should go for identifying the land suitability criteria should be applied, and with the help of this land suitability, by taking all the aspects, like taking all geological consideration, the slope, the approachability from the village, the road connectivity and the rainfall conditions and geological condition, the geomorphological aspects and all, we should go for identifying the land suitable for making the roads in that area, which will be away from the river bed, which will be away from this type of damage. And when this type of globe scenario will take place, this connectivity, we will not lose the connectivity, because we are far away, our roads are far away from the river bed. So, that is why future modeling is important in this area, and now we have the good softwares available in the market, through which we can model. The research organizations are developing their own software, and they are modeling this type of scenario if this 3D modeling is being performed for this outburst, glacial lake outburst phenomena. And if you will see here, the Leo village before and after Parichu globe in 2005, as I have discussed, that this map is the first one is the upper Leo village, which is now being developed quite extensively, and the lower village reded portion is basically damaged part of the Leo village. Earlier Leo village was looking, the B map is showing the earlier Leo village. You can see here that in the B map you will not find the settlement in the upper part of the Leo village, but in the A map you will find now the moving of the settlement towards the upper part of the Leo village. If you will see the C map, you will find the houses which has been destroyed, and the this cultivated land which has been destroyed by this Parichu lake outburst flood. And this Parichu lake outburst flood also resulted into the damage and the shutting down of the Naptha Jhakri hydropower project also, because of huge amount of debris and water came and resulted into the shutdown of this Naptha Jhakri hydropower project in that area. So, I tried to find out what is the impact of this livelihood of if this type of hazards, or if the snow cover is changing, if the snow cover is decreasing, then maybe the free lands are being utilized by the herders, and they will be helpful for them. But the scenario is different there. According to a respondent in Jayatram, herding their sheep and goat nearby the Chandratal lake, has given his opinion that 20-30 years ago his father used to own more than 500 sheep and goat, but now he has only 275, and the reason is the shrinking of good pasture land. He told us that the snow free land in the area has been on increase because of fast melting of glacier and snow area, but these are all wasteland, thus no use for them, as good quality of grass cannot thrive on these rugged rocky land. So, whatever the area is being freed by the recede of the glacier or recede of the snow cover is not of use, because they are all the rugged terrain where no good quality of grass can thrive, and that is why these sheep and herders are not getting much benefit of the retreat of this snow cover or the glacier. I have mapped the geohazards along the river Spiti and Satluj after Parichu globe, and you can find here that from Sumdo to Poo area, this area is there, and the damage of road, bank erosion, channel blockage, active landslides, bridge damage, and the settlements, road and river has been mapped here. You can see here that from Sumdo to Poo you will find the most damage, and at the Khab when the river meet into the Satluj, because of the river Satluj is bigger in size, so it accommodated the water of that Parichu lake outburst, but because of the debris and all resulted and huge amount of water, the Naptha Jhakri even quite far away from this Leo area, the Naptha Jhakri was affected by this, and in between there was a formation of a small Lolof type of situation, landslide lake outburst flood. which is a secondary lake outburst. When this type of big lake outburst take place, secondary blockage in the river valley took place, and this secondary blockage resulted into the formation of a small lakes in the river valley itself. And these small breaks certainly after 2 or 3 days outburst took place in that small lakes and resulted into huge amount of water release in the low lying areas. So, these are some of the examples, and then in concluding we can say that the climate change in the region is resulting into the decrease of areal extent of the glaciers, and glacier lakes in the region are showing increase in its aerial coverage, leading to increase in potential threat to the region in the form of GLOF. And participatory GIS, where we can participate, like people and the government organization and civic bodies all should participate. So, to effectively and this participatory GIS can be the effective tool for inventorying glacier and glacier lakes, identifying its potentiality and mitigating the adverse effect on livelihood options in the downstream region. So, glacier retreat is resulting into the formation of certain glacial lakes, and these glacial lakes pose damage to the nearby region because of the outburst phenomena taking place in the region. And if we will see the study performed by certain research scholars, we find that now the GLOF situations are becoming prominent, and day by day in coming decades they are going to be a major threat in the mountain area, because too many glacial lakes has been demarcated as potential threatful lake for outburst. So, we have to go for seeing the dynamics of the snow cover. We have to go for a study of the dynamics of this glacial lake behavior, and with the help of these we can chalk out a better plan. We can devise a plan to mitigate the adverse impact of the GLOF phenomena in the mountain. Thank you.
Thank you so much, sir. Thanks a lot for this very interesting lecture. And friends, we have today talked about GIS and glacier environment and the use of GIS in glacier environment as such as in quite depth. So, friends, with this we take your leave, and we must thank sir for being here today. Thank you so much, sir.
Thank you.
And thank you, dear friends. Keep watching us.